Good. So first, I would like to thank the organizers for this lovely workshop, and it's nice being in this campus and visiting India again at any opportunity. So, okay, until now, we basically heard about work on systems where there were some charge modes and neutral modes, and I think I'm the first speaker to talk about a system where there are no charge modes. So charge is completely frozen. It's an electric insulator, but nevertheless, there can be some excitations that carry, and particularly in the spin sector, and therefore, one of the most practical way to probe it in transport is in thermal transport. So I'm going to talk about thermal Hall effect in chiral spin liquids. The work that I'll discuss is just very recently published, and it's with my graduate student, Pasha Tikhonov, who just graduated. Okay, so first, a brief outline of my talk. I will start with some introduction, a very brief introduction to the concept of spin liquid and chiral spin liquid in particular. And then I will mention some experimental results on thermal Hall effect in such systems. I stress that I don't have any ambition to explain the experiments, but I will mention them because I think in the model that we have studied, there are some features of realistic systems that you can see. So then I will describe our model, which is basically a study of a toy model on a Kagome strip structure. And I will discuss the quantum phases that that you can get in such system, and their signature in kappa xy, that's the thermal Hall effect. And there is assumed to be a tuning parameter in our system, which is an external magnetic field. So, okay, brief introduction to quantum spin liquids. So, the prototypical platform to observe exotic spin systems is materials or some structures where you have frustration of the exchange interaction. So if you take the Heisenberg model, in the case where the coupling is ferromagnetic, of course, it doesn't matter what is the crystal structure. You can have a ferromagnetic ordered state, but if the coupling is anti-ferromagnetic, then in some frustrated lattices, and particularly in the case where you have many triangles, you may have the phenomena of frustration. So what is frustration? I'm sure you've seen it a lot. If I'm trying to order spins to satisfy the anti-ferromagnetic coupling on a single triangle, then the third spin will don't know where to go. And classically, of course, you can minimize the energy by some configuration. But then if you look at a structure that is particularly frustrated, like the Kagome lattice, so this is a Jewish crystal, as it's called in certain communities. Although in India you can see it, right, in many important monuments. So anyway, in such a structure, notice that ordering or minimizing the energy for one triangle still leaves a lot of freedom for the others because it's so sparse. And then if you just think of classical spins, you get a huge degeneracy of possible ground states. However, quantum fluctuations can give us more interesting configurations, and in particular, so what do I mean by quantum fluctuations? Notice that if the spin are operators, quantum operators, the Hamiltonian contains non-commuting parts, and therefore you can get a situation where ordering one component of the spin leaves others uncertain and so on. So you can have other solutions for the ground state that have better energy than any of the classical candidate states. And in particular, you can get something like that, which is a so-called valence bond crystal. So it's a state that is still ordered. It breaks translation symmetry, but on each bond, you create a singlet. And still, you can have different singlet coverings of such a structure. So a more exotic option is that you can have a coherent superposition of many such coverings, and that gives you something that is named the spin liquid. So I found this is the best picture I found to convey it in Google. Basically, it's some state where there is no obvious ordering of the spin, and it may not have any local order parameter. It can still have some topological index, but no spin ordering. Okay, so it's called the spin liquid because if you think of it intuitively and translate it to a language of quasi-particles, it's possible to map spin operators and the parameters of the spin system to some language of effective particles. And in particular, the spin operators S plus minus can be loosely mapped to creation and annihilation of some effective particles we call spinons. And why I say loosely speaking, because usually depending on what is the statistics, you have to introduce some gauge factors to satisfy the commutators properly and so on. But basically, this is what it is. So I can introduce spin-on particles. You can assign a spin-on density to the SZ operator. And as a result, if there is an external Zeeman magnetic field, it appears in the Hamiltonian of the spinons as a chemical potential. So I can think of a magnetic field in the real world as some fictitious chemical potential for the spinon, and time reversal symmetry or some time reversal transformation in the spin system corresponds to particle hole in the spinon system. Now, similarly, you can construct other spin operators, which would have, in the language of the spinon, the significance of current. So now the next thing you can suggest, if we can consider the system of spinons and talk about densities and currents and chemical potential, maybe I can also introduce something that will act like a magnetic field. And that's the next thing that I'm going to tell you. And if you, so there is some freedom. So you can define bosons. I mean, of course, the transformation is not just S plus equals A dagger. Okay, so so either hardcore bosons or fermion, Jordan-Wigner fermions, but then you'll have to introduce a string if it's in one dimension.
But I don't understand the freedom. I mean, they are derived from some spin operator.
Yes, but in order to define properly the particle operator with given statistics, you may have to introduce some gauge fields. Like the Jordan-Wigner is a concrete example that is very familiar, right? So in order to get the anti-commutators, you have to multiply this by a string operator, okay?
So you're talking about 1D?
Eventually I will talk about quasi-1D. I will talk about a coupled chain model, but now it's just in the introduction, okay? So I'm being very general, okay? But in the literature you can actually find mappings to bosons, especially in 2 dimensions. It's actually more convenient. Yeah?
So I have another question. I mean, you defined the spin-on density as SZ, right? So the
Yeah.
form of the spin-on current should be actually Hamiltonian
Yeah.
in such a way that it satisfies the continuity relation with SZ.
Yeah, yes, that's
This is for some specific.
Yeah, that's for actually, you're right, that's for specific Hamiltonian. Eventually I'll get to my model and there everything is defined, but okay. So, good, so if we can talk about a system of spin-ons with something that acts like or plays the role of a magnetic field, then maybe we can have things that are going to be analogs of the quantum Hall effect for these neutral excitations. And indeed, such states were proposed in the literature. So this is one of the, I don't know if earliest, but one of the early suggestions. So Kallmeyer and Laughlin had a Q-type, yeah? That's right. So actually, okay. So this is actually from Kallmeyer and Laughlin's paper. So here the A dagger. These are some bosonic operators.
Right, but
they're not spin-ons. Okay. So it's a matter. Okay. Actually, the.
I think that you have done from this harmonic picture, no?
So I'm saying so if you're working in a model that is one-dimensional, maybe the useful representation would be Jordan-Wigner fermions, okay? But now there's also a matter of language. So if they are bosons, usually you call them magnons and not spinons, or. Okay, no, you're okay. Thank you for the comment. Yeah, that's right. So I'm just mentioning this as a background because I will not follow up on this, but this is perhaps one of the first concrete examples where you realize something that, or at least try to realize something that is claimed to be a chiral spin liquid. So what basically Kallmeyer and Laughlin suggest is that you can map the Heisenberg model on a triangular lattice. This is on a triangular lattice to the mu equal to bosonic Laughlin wave function. Mu equal half, sorry. Mu equal half, yeah. So, roughly the way to do it is that you can map the spin XY term to some tight binding kinetic energy, but then this kinetic energy has to be defined in a way that will have a proper positivity condition, and it turns out that you'll have to introduce phase factors, but these phase factors for okay, let me. Okay, so exactly the next picture in my slide. So you introduce some phase factors that in this model are only plus or minus, and they're different on different bonds. And actually, I don't have the full lattice here, but on each triangle, you have 1 plus and 2 minuses, okay? And if you look at the total flux that is enclosed in such plaquette, it turns out to be half a flux quantum, or equivalent to half a flux quantum. Okay? So, and you can decorate the entire triangular lattice with this. So in any case, this is a cute idea, very beautiful. You can write down a trial wave function, which is, as I said, is a mu equal half bosonic Laughlin state. However, we know that it's not the ground state of a triangular lattice antiferromagnet. And one thing that is to note about this model, that you can have here something that has the significance of a flux, but it's very restricted. It's only pi flux. So can you have something that will provide an arbitrary or different values of flux? And indeed it turns out, so that's a question. And indeed you can do such a thing, and in particular in systems where there is a strong spin-orbit coupling, there is, in addition to the standard exchange interactions, you can find something that is called a Gialoginski-Moriah interaction. So it's mediated by spin-orbit coupling, and D is some fixed vector that depends on the. So, for example, in many two-dimensional systems, it may be perpendicular to the surface. And if you look at the form of it, it's actually analogous. Once again, if I map it to a Spinon or to Magnon language or whatever, then it's this D can be associated with some kind of a gauge field, and it can take different values. And I also want to mention another collection of all the work where they propose that if you have such terms in your Hamiltonian, and in addition the exchange interaction, you can generate a lot of higher order, if you like, kind of terms. And then it may be possible in a system where in such a system where you have this kind of chiral interaction terms, you can have a chiral order parameter, and that can acquire an expectation value, and basically it corresponds to some kind of a circulation of 3 spins on a triangular structure. And if such an order parameter exists, then you can have a chiral spin liquid, and it's a state where both time reversal and inversion symmetry are broken, okay? And they can be broken either spontaneously or by some external parameters, say external fields. Okay, so this is just a brief summary of the concepts that I'll be referring to. Now for the thermal Hall effect. So there were a lot of beautiful talks about it, but let me just briefly mention a definition of what we call a thermal Hall effect, kappa XY coefficient. So if you have a system that has some kind of conducting or propagating excitations in a temperature gradient and in the presence of a magnetic field, in addition to the longitudinal thermal conductance, you can have heat flow perpendicularly to the thermal gradient, and that coefficient is defined as kappa XY. And in order to have such things, you need to have some excitation, not necessarily a charge, that has chirality, and therefore in the presence of the field, it will tend to generate a perpendicular flow. So it's I assume a very difficult measurement to do in practice, but it has been done on a variety of magnetic compounds. And I mentioned just two. Of course, there are a lot of them, especially in the last year. But this is from 2015, the group of Fuan Ong in Princeton. And as you see from the title, they call it a Kagome magnet. So, and it's some kind of very long formula compound, which contains copper atoms. So this is the source of the spin half. And anyway, that's the data. So what you see here is a kappa xy measured as a function of magnetic field. It's anti-symmetric, and it's non-monotonic, and it varies with temperature in a way that actually is quite complicated. So it may change sign with temperature and magnetic field. I mean, for given field, it can change sign when you cool down. So there's a lot of structure here, but notably, this compound is an electric insulator. So the magnetic field here does not play the same role of as it is in electric conductors, but it allows you to break the symmetry and give you a thermal Hall effect, and the neutral excitations must be responsive to magnetic field. So, you know, the only thing you can think about that it must have to do with the spin excitations in this compound, which indeed has the Kagome structure. Okay, another example, more recent, is and once again, I'm amused that in the title they put a model and not the material, but it's some compound that is believed to be realization of the Kitaev model for spin liquid. So this is very different from the Kagome antiferromagnet I discussed before. It's a very special model. It's quite amazing that there are indeed apparently realizations. So it's a honeycomb crystal where on each bond surrounding, each of the three bonds surrounding a site, there is only YY, ZZ, and XX interaction. Okay, so this is the model, and it's a rare example where you can actually solve it analytically and find and map it to some free fermion model. And in fact, it is predicted to have in some regime, depending on the parameters of the different J's, a spin liquid state. And this is a measurement of the Matsuda group. Once again, it shows kappa xy as a function of magnetic field at fixed temperature. And what you notice here is that there is a plateau. And the plateau is at 1/2. So if you look at the right-hand side axis, it's in units of what was called kappa naught in the previous talks. So it's 1/2. And this is claimed and advertised to be a smoking gun indication for Majorana mode, which is predicted for this particular model to be. So there is a Majorana mode, I mean, according to this, but I want to point out something important about the data. By the way, I heard that there are some, Yes? Yeah, okay, good. Thank you. So actually you can see it here. So it's smaller than, it's smaller, yeah. But, no, so actually this material, I mean, they don't, okay, so this material turns out there were a lot of measurements done to dictate the exchange interactions some of them by Amit Keren, our colleague from the Technion, and in fact, it is a ferromagnet. It's not an anti-ferromagnet. It has a Kagome structure, but it's a ferromagnet. Okay, so this was just to demonstrate that you can get, I mean, it's certainly you do not expect to see here anything quantized, and particularly they are not so low temperatures also, okay? So, okay, but here you see, these are actually also not, you are right, yeah, they're also not low temperature. I heard that there are some reservations about these results, that they were not reproduced by other groups, so I don't know, I don't want to get into, but it is relatively recent, just from last summer. But what I want to point out that, let's take it for granted for the moment that we believe the data, we see that this plateau is observed only in a very narrow, in fact, range of the magnetic field. So at zero magnetic field, you don't see it here, but at zero field, basically, okay, at zero field, of course, it's a zero, but you see much lower values, and it approaches this plateau only in a very narrow range of field, okay? And, okay, so this is just a very, very, very general motivation. Okay, now for, yeah, that's what I just said, that there's this plateau in a narrow range. Okay, so now I'm coming to our model. So we basically, originally, I must say, motivated by the Ong experiments, before I knew much about the system, we wanted to see if there is a simple toy model with tunable parameters that can capture some of the behaviors, and presumably such a model may not give you a single phase. So the thermal Hall effect may be indicative as you tune, for example, a magnetic field or temperature, you may be able to tune through different kind of quantum phases. Since I have a lot of experience on one-dimensional models, we were looking at a coupled spin chain model. So in fact, I should mention there are a lot of earlier works on such constructions where they were able to show that you can, in principle, realize a chiral spin liquid phase, and where this order parameter that I mentioned, the chiral order parameter, is irrelevant in an appropriate regime of, under appropriate conditions. Okay, so what we are doing in our model is the following. I'm considering a quasi one-dimensional model that is basically a narrow strip of the Kagome structure. And we chose it, as I'll show you in the next slide, in a way that seems to minimally capture the symmetries of the stars of David that appear in the Kagome crystal. And we are assuming that there are two external fields, if you like, at least one of which is tunable, which assist and in fact tune the amount of breaking of time reversal and of parity symmetry. One is a magnetic field, and the other is this Dzieloszewski-Moria parameter, and usually it's just given by the sample, so it's something, but we assume it's there and that it's not small. So, okay. So here is the model. We take a strip of a Kagome, so assume that it's infinitely long in the x direction. but in the vertical direction, it has 6 triangles. So in this respect, it recovers the 6 distinct triangles that you have in the single Star of David. And in fact, to complete it into a periodic 2-dimensional structure, you have to add one more element. So I'll maybe discuss it in the end, but at the moment, let's just stick to this. And in order to be able to treat it as a 1-dimensional model, let's now introduce a distortion, some kind of a bond distortion, which turns it into 3 coupled spin chains. So I should also stress it's spin 1/2. And the 3 chains are not equivalent. So what are the chains? The top and bottom ones are meandering along these strong bonds. The middle one has a higher density in the unit cell. So they don't have the same parameters, but there are 3, you can treat them as 3 coupled chains. So let me just give you some dictionary of what I have in the picture. Each bond corresponds to an exchange, anti-ferromagnetic, or actually a general exchange interaction, and it assumes some XXY anisotropy. Each triangle contains this little circle which denotes the DM interaction, and D is assumed in the Z direction, okay? And there is also a Zeeman magnetic field. So these are the ingredients, and then what we do is we map it to a 3 chain. In fact, each chain is described by a Latinger liquid, and there are some couplings between them. And the way and now I'm using, I'm coming back to all these questions of how to map the spin to spinons or to particles. We use the standard bosonization of spin half operators on each chain, and there is a chain index L. Okay. Okay. Good. So this is the Hamiltonian. Actually, it's a low energy Hamiltonian, which neglects a lot of things that are not important for us. And as I mentioned before, because of the way we defined the chains, so if you look at each of the uncoupled chains, first of all, it's a Latinger liquid with some additional terms, but the Latinger parameters are different. But they're just parameters, okay? And they're just given by not only the XXZ anisotropy, but also notice that if I go back to the slide, you see that in each of the chains, there are also next nearest neighbor couplings. So, but you can always define some effective Latinger parameter and velocity and so on, and you can write basically all terms in bosonization. And I would like to stress several things about the important terms in this Hamiltonian. So the most important one, essentially, that eventually will give us the chiral spin liquid is something that can be written in this form, and it essentially corresponds to this chiral interaction. So another important ingredient of our model, as I said, we have 2 parameters, the magnetic field and the DM coefficient of the DM interaction. And notice that in the bosonized form, they primarily appear, I mean, that's not their only contribution, but they appear, they give rise to some linear term in the grad phi and grad theta fields. Now, grad phi, for those of you, most of you are experts in bosonization. This corresponds to density, or at least the smooth part of the density operator, and grad theta to a spin. And because they are linear, they can be absorbed by a gauge transformation. But as soon as you do that, the cosine term will acquire some oscillating phase shift. So this is pretty standard. And in fact, in order for, anything that can give us an interesting phase that is not just coupled Latinger liquid has to do with these cosine-like non-linear terms. And in order for them to be relevant, you need to suppress these oscillations. So first we have two such terms. One of them is becoming frustrated as soon as we put a little bit of magnetic field. And in fact, at zero magnetic field, I'll tell you soon what it gives, but it's essentially giving some kind of a valence bond crystal phase when it becomes relevant. The chiral term, on the other hand, has to satisfy some commensurability relation between the B and the D fields in order to suppress these oscillations. So this already starts to smell like something similar to what we have in quantum Hall state. And this is essentially the phase diagram that we get from it. So at very low, so the parameters here, K is some Latinger parameter that parameterizes basically you can think of it as the anisotropy, the XXZI anisotropy. And the vertical axis is magnetic field. And experimentally, if such a system can be realized and measured, this would be the tuning parameter. We get three prominent phases. At sufficiently low magnetic fields, there is a valence bond crystal, so it's this dimer crystal that I mentioned before, and it also is restricted to some value of K, which is relatively small or smaller than 1/2. And there is a critical field where basically there is a commensurate incommensurate transition and it is suppressed. The second exotic phase is the Chiral Spin Liquid, and it turns out that this is centered around K equal 1/2, and it depends very sensitively on the magnetic field, and in particular, it's centered around a particular field I call BD, which is proportional to D, the DM interaction parameter. And if you remember that B here plays the role of a chemical potential, D plays the role of magnetic field, quote, or flux. So this ratio must be 1/2. So if you want to define some kind of a spin-on fraction, it would be this ratio, okay? So that's a chiral spin liquid that it is analogous to a quantum Hall state.
What was the MSL?
And the MSL, okay, good. The MSL is a metallic spin liquid. So this is what you get when nothing is relevant and you just have some three coupled Latinger liquids, and it has power law correlations, and it has, okay, as you'll see. So it's not going to give you anything quantized, but it can give you a thermal Hall effect.
But the Chiral Spin Liquid is gap.
The Chiral Spin Liquid will give you, I will show the kappa xy soon, it will give you a plateau. But it's an integer plateau, so there's no Majorana is here, okay? So you'll see it in a... So what is gapped is some combination of the chiral fields. It's a... Yeah, you're left with edge modes, yeah. So in fact, this caricature more or less describes what happens. So there's a left mover and right movers that are enslaved to each other, but there's a leftover right mover and left. Oh, sorry. Yeah. Yeah. So. Okay. Here is okay. There is some RG equations that describing the where you expect, how do we get this chiral spin liquid regime in the phase diagram, and this is what it looks like. These are the RG flows. Interestingly, so in addition with, there is a range of K's where the coupling coefficient tends to grow, so it's relevant. But in addition, K tends to 1/2. So there is some margin, there's some range around it. I don't have an expression for delta here, but okay. This is how it looks like. And given that we have these, so we have these three phases, and now the next thing we want to do is to calculate the thermal Hall effect, just from the definition. But in our geometry, the way to do it is, or the easiest way to do it is to assume that somehow there is some superhero experimentalist that can make the top chain at equilibrium in some temperature T1 and the other in T2, and you can measure the heat current along the x direction. Okay, just what I had in my caricature. Since I'm a theorist, I'm allowed to assume it. Okay, first of all, we have to, of course, define a heat current, and it's defined via the continuity equation for the energy, and it has actually, it turns out you can easily show that it's completely quadratic in terms of the bosonic fields, regardless of whatever complicated terms appear in the Hamiltonian. It's actually a very... H is the Hamiltonian density. Okay, so you can always write the Hamiltonian like that, and basically the right-hand side is the commutator of capital H, of H and little h, okay? And okay, and this gives you, this is pretty standard, by the way, in a Lattinger liquid. It has been derived. Anyway, so, yeah? Mm-hmm. Okay, so in this system, the bulk sample is sort of, there is a very, there is, you're right, there is no bulk sample, so to speak, unless you can call the middle chain a bulk, okay, but it's itself one-dimensional. If you can duplicate this, and I'll mention later how I think you can do it, and maybe you can relate it to a more realistic system, okay? But at the moment, it's really academic, so I'm just assuming that there is an imbalance. So, of course, if...
I don't understand. I mean, follow up on this here, you don't have the...
I have it, so, okay, what I have is that only in the chiral spin liquid, so let me get to it, okay? I first mentioned what is the calculation and then what is the result, okay? But you are right, there is, at least in this phase that I called metallic spin liquid, you can still calculate this, but it gives you something that is not edge, and there's no edge and bulk. I mean, I'm not claiming that you always have edge and bulk.
No, I don't, I mean, how do you separate in your calculation between what happens in the bulk and what happens at the edge.
I don't separate. You are insisting on it because you're thinking quantum Hall. I don't do that.
I want to think about the middle chain as the bulk.
You can say, that's what I said. In practice, right. So in fact, this is exactly what, because I have 3 chains, not 2. I mean, it's a very degenerate bulk, I agree, but still in the chiral spin liquid phase, because we have this gap opening up, we can actually do this. And yeah.
Back to the previous slide.
Yeah, sure.
There you see the middle 2 are gapped, right?
Right.
But then there's some symmetry that's preventing the outer 2 from being gapped.
Yes.
What is it?
So it is the break. So I said that we are explicitly breaking both time reversal and inversion symmetry by this D and B fields, and there is a commensurability condition, and depending on the sign, if I keep the sign of D and I just flip the sign of B, everything will reverse, for example. Okay. So.
The question is, if there's some higher order term, you should write down, get out the top and get the bottom.
Exactly. That was the question.
You do quantum Hall and eventually you can get.
Good. Yeah. Right. So okay. So we don't. So there are a lot of terms, but at least as long as you keep the system, as there's no disorder, and that's an issue. As long as there's no disorder, so you have a lot of chiral-like terms with different commensuration conditions. And this turns out to be the leading one that can open a gap. This one that I took into account. Okay.
The statement would be that for top and bottom edge, your commensuration condition would be different and it would not be satisfied. Therefore, you would
That's right. Yeah. Yeah, that's right. Yeah.
Something like chiral anomaly, which appears in quantum Hall?
What do you mean by chiral? So, I'm not sure. Okay, maybe ask me again at the end. Okay, so at equilibrium, you are going to get, in fact, what we see technically in the calculation is that in each of the 3 phases, we do a different calculation. But in each case, it turns out that there are 2 sectors that contribute, one coming from the top, or some combination of the top and middle, and the other from the bottom. And at equilibrium, they give you 0 current, as you expect, but once you put a temperature gradient, there is a net heat current, and that's what's giving the result. And now I just plot the final result. So it's really a bit sketchy. Oh, sorry. So now notice that this is the phase diagram, but now it's inverted so that the vertical axis is magnetic field. And we imagine driving the magnetic field from 0 through this black line. Then what you see is this is kappa xy over t as a function of b. At very low magnetic field, it gives you nearly 0 up to exponentially small correction, and that's the valence bond crystal phase. So essentially, it's an insulator. Okay, so it's a thermal conductance and thermal Hall conductance are 0 or nearly 0. Then there is this metallic spin liquid I mentioned, which gives you something non-universal, but as soon as you get to this narrow range of fields where the commensuration condition is not strongly violated, so it's centered, as I said, around some magnetic field that is proportional to D. Then you get a plateau, and the plateau is, in my units, it's pi over 6, which corresponds to 1, not half, okay?
So that's the limits of the
its unit, so the units are of kb square over h bar. That's why it's pi over 6 and not pi square over 3, okay? Okay, so, and then the intermediate region, there's nothing universal, and it depends on the parameters what you exactly get. So this is a very sketchy way of interpolating. Yeah, so as I said, the kappa xy for the metallic spin liquid region is some complicated function that depends on all the parameters, and it has the correct symmetries. Yeah?
So the metallic one, I thought there was the one with all coastlines are relevant.
That's true. But you have some, quadratic couplings between both chiral and non-chiral between the channels, and therefore, essentially, what this is so there is some also just longitudinal hole conductivity along the.
On a practical level, so you want to compute with purely quadratic.
Yes.
You start with non-zero trees, so the rationale is you just put in these trees to normalize quadratic couplings.
Yeah.
And throw all the trees away.
Yes.
And use the quadratic action.
Right. That's right. That's exactly right. Yeah. So the details are in the paper. And the result, I'm showing just a few curves. As you see, they depend on the parameters. Also, the sign, in fact, you can get, depending on the parameters, you can get negative signs, and you can get a sign change of kappa xy. So that reminds very much of, in fact, what the Ong group got.
So this figure is supposed to represent something like the wire construction of this thing?
It is, so as I said, it's once all the cosine terms are irrelevant and you have a quadratic theory, it's just 3 non-chiral channels coupled by coupling terms, and the coupling terms include also chiral terms, okay? So they're not just grad phi, they're also grad phi, grad theta kinds of. That's what I did in the beginning. That was my initial, that was the initial. But this is for the phase. This is only for the phase which I called metallic. Okay, okay. So basically, you get some non-universal function of the parameters times t. That's as we expect. So let me summarize. So we studied the phase diagram of coupled spin-half chains model on a Kagome strip structure with a magnetic field and Dzhalozinski-Moria interaction. And this is what we get, a phase diagram which contains 3 phases, and each phase has its signature in the transport. There is a spin-on insulator phase, which is the valence bond crystal, and it has vanishingly small thermal Hall conductance. There is a metallic spin liquid, which is just quadratic excitations, and some coupled Latinger liquid with chiral terms, which gives some non-universal kappa xy. And there's a chiral spin liquid phase that is restricted to a narrow region in the phase diagram. And in particular, it's centered around a particular value of the field that satisfies some rational ratio between these 2 fields. It is, in a sense, analogous to a quantum Hall filling factor, where the numerator represents the density of the spinons. In fact, the density away from the particle Hall time reversal point, and D is the analog of a magnetic field in a sense. And then you get a quantized thermal Hall effect. Okay, so just briefly some outlook about extension to 2 dimensions. So, which would be the full wire construction, if you like. As you notice, if I just take my Kagome strip the way I defined it, which is this 6 triangles, it's not closing on itself, so it doesn't give me periodic, the full period in the vertical direction. So in order to extend it, I need to add 1 more chain. That's all. And then you can basically duplicate it. So essentially, I mean, we didn't actually study it in details, but it looks like under the conditions that I mentioned that you expect to get this chiral spin liquid phase, the additional chain will just act like a non-chiral independent mode. And the next strip will give us, just duplicate the same result, so maybe it can be extended to the full-fledged 2-dimensional structure. But notice that we had to assume for this picture to hold some distortion of the Kagome lattice. So if all bonds were completely equivalent, I'm not sure. I mean, basically, you need something to break the symmetry in the vertical direction to get this. And there are some issues. What happens when you introduce disorder? And that's, of course, the initial thought is that it will just kill everything. But it's not so clear because there are other, in fact, topological chiral terms that I didn't actually, this is something we discussed with David. These are things that if they become relevant, it's not really clear what they're doing. They're not giving an expectation value, but they're typically frustrated. If you don't have disorder, they're frustrated. But if you have disorder, then you can have, in addition to the disorder itself, additional things, and you need to do a more elaborate RG to study. So I'm not sure what it does. There may be a competition. And then, okay, about experimental data, the first thing is to find, so of course, as I said, I didn't have the ambition to explain any experiment. I did show you experimental data on a system that is not described by this model, but nevertheless, it has this feature of a plateau, and a plateau in a narrow range of fields and so on. And you know, since many of these compounds have a strong spin-orbit interaction, I'm assuming that you cannot neglect such terms, such things like the DM interaction, and maybe some features can be captured by such models. And there are actually new compounds that were very recently studied, but yeah, that's what I have to say at the moment. Okay, thank you for the attention.